So today we are going to discuss about the astrophysics topic, and this topic is going to be on the radiation chapter. And in this particular video, we are going to discuss about some basic definitions of the radiation terms and all that stuff. So let's start with the basic definitions of how we define the radiant energy which is flowing through a cross-section area of d sigma. So let's see in this particular diagram, there is a radiation which is making an theta angle with the normal to this particular surface, which is of the unit area d sigma, and the solid angle which is subtended by this particular radiation is equals to the d sigma d omega, as you can see here, and making an angle theta. So how we can relate these particular quantities with the radiant energy which is flowing? So the fact is that there is a very well known particular formula for this stuff, which is the small amount of energy, let's say, which is dE, is equals to the I, which is the radiation intensity. We will try to rediscover that what's this particular thing is. I cos theta d omega d sigma dt and d mu. So here, as you can see that this particular term, there is also one more thing, that the in frequency of this particular radiation, which is frequency of this particular radiation, is from mu to d mu, which means it's between these two particular quantities there is radiation, this particular frequency. So this is how we are going to define our this particular energy which is flowing through this particular cross-sectional area. And the fact is that here this particular solid angle, as you can see, that we can write this particular solid angle in the polar coordinate form, and there is also a very well-known formula for this, that how we can write this particular term, which is a solid angle, in the polar coordinate as sine theta d theta and d phi. So maybe you are not familiar with some sorts of mathematics which I'm going to use in this particular video. So don't worry, I'm going to also start some of the mathematics which is useful for the astrophysics. Like what is phase function in the astrophysics? Because phase function is very important when we are going to discuss about the scattering of the radiation when it is passing through some medium. Okay, so it's like a bit of mathematics, and some mathematics like double integrals and triple integrals, all that stuff. So in this particular video, there is not some sort of very high mathematics, but from next video, you can guess that there will be high mathematics stuffs. So be prepared for that. Or if you want, I can make the video on that particular stuff. So let's start our topics. This is how we are going to define out the solid angle. So this term which I have written here, let's try to understand what is this. You know what is this? This is solid angle, no problem. This is d sigma, which is this particular cross-sectional area. And this dt means the energy which is flowing in the dt time through this particular cross-sectional area. And d mu is the frequency of that particular radiation. But the fact is that what this particular quantity I have written here is. So we are going to discuss about this particular stuff, I. Okay. So here, this I is commonly known as radiation intensity. So there's a lot of confusion that what's exactly the meaning of radiation intensity, because in some books this is defined as some different. So I will try to clarify that what is here radiation intensity. Radiation intensity. So this is the meaning of this particular I. What is this? This I, okay. This I am going to discuss here. So this particular I is the radiation intensity, which is defined as the radiant energy which is flowing. So let me write it here, that I is defined as the radiant energy, small amount of radiant energy, which is flowing to the cross-sectional area d phi, and subtending the solid per unit solid angle d sigma, and unit interval of frequency d mu in a time dt. So this is how we are going to define out that what is the radiation intensity in this particular stuff. In some other books, you will probably see that the radiation intensity I is defined as d phi divided by d phi divided by d sigma, sorry, d omega, which is the flux per unit solid angle. And in this particular context, it is not only for per unit solid angle, it is also for the per unit frequency, means the unit frequency per unit time, per unit surface area, cross section area. So this is how we are gonna define this particular stuff. So now let's move on. And generally, we are going to find out that the particular term that I have written here is only for a particular direction. What if someone asks you that I want that the radiation which is in all directions I want. This is only from the particular direction radiation. I want the radiation defined as in all of that particular direction. Then how you are going to define that particular thing, we are going to discuss here. Okay. So don't confuse between these two stuffs. This radiant energy is similar to this particular d phi. Okay. I have written here because I have defined here radiation uh, power as E. That's why I've written here. Or you can say that this stuff basically is this. Okay, so don't be confused between these two stuffs. Okay, so this is how it's defined, radiation intensity. Okay, now if you see, I want the radiant radiation energy flow in all of the direction. What I want to do, you have to just integrate all the stuffs. So the left hand side stuffs were integration of I cos theta, and here it is d omega, d sigma, dt, and d mu. So when you do the integration of this particular part I'm taking, you can say that our d sigma, dt, and d mu will not contribute to any of this particular stuff, and you will have only the integration of I, because I is dependent upon theta, phi, and theta, and it's equals to the d phi. And if you are gonna substitute the value of d phi, because I have defined that d phi is nothing, d phi is sine theta, d theta, d phi. So this is how we are going to define it. So when you do this, it will be like d sigma, dt, and d mu, and it's like the integration of I, which is a function of both phi and theta, and substituting this will result it as sine theta, d theta, and d phi. So this is what the stuff is. And if you carefully do this, this particular term will yield this term. This subscript is mu, nothing to worry about it. And I phi theta, sine theta, d theta, d phi. But the fact is that it will change from one integral to double integral because you have two functions, which is phi and d phi. So one integration is from 0 to pi and one integration is from 0 to 2 pi. Because the d phi term, this is d phi term, because the d phi terms can take values from 0 to 2 pi and d theta can from 0 to pi. Okay. So this is your integration term. So here you can see that there is some unknown variable, which is here, as you can see, this particular f. So this f is nothing. No need to worry about this f. I'm gonna show it here that this particular f is nothing. It's called the net flux. And net flux is what? Power per unit time. So this is how we are going to define the net flux. So in this particular scenario, this particular FB, this particular F is defined as, the radiant energy. So I'm going to write the flux as phi. So radiant energy, which is d phi, small df, and if you will integrate it, it's like phi, which is the radiant energy per unit frequency, mu, and per unit area. So this is how you're gonna define these net flux. These are the basic terminologies, that what is net flux, and the power, intensity, radiation. So there's a lot of misconception between peoples behind the knowing variables of these particular stuffs. The fact is that this particular FB here is the radiant energy which is flowing per unit frequency and per unit area. So this is what the basic definition. If someone asks you what's the total flux, so you can find out the total flux in this particular fashion by doing the integration. How? So if you can see here, as you can see here, and if you ask that how I just equate this particular quantity as pi into the net flux, so there is a whole integration process that you have to do, and you will get this particular value. So it's not the today's topics. So in today we have to find out the net flux. So net flux can be found out as FB, and it is equal to the, if I do the integration of d phi and d theta separately, it will yield as, when you do the integration from 0 to 2 pi of d phi and integration from 0 to pi. Now it's not dependent upon phi, it's I dependent on theta sine theta d theta. And it will carry on the whole integral. It will yield as pi f subscript mu, and it is equals to the, when you do the integration from 0 to 2 pi of d phi, it's 2 pi, and it's the whole integration from 0 to pi of I theta sine theta d theta. So this, and when you cut down the pi on both sides, you will find out that FB is equal to the integration from, 1 minute. Your net flux is nothing, it's just integration from 0 to pi to I theta sine theta and d theta. So here, as you can see, that I have defined out, you have to find out the net flux, and this is a way to find out all of the net flux situations. So let me quickly verify, let me see it if I have done any of some sort of mistakes here. Because one term is missing. Okay, so when I have defined the d phi, I think I have not written the cos theta down. Okay. So cos theta is everywhere missing. So sorry for that. Cos theta is everywhere missing. I don't know why I have done this. So the fact is that you have to just add here. Let me write it with different color. Okay. So you have to just add here cos theta. Okay, that's my fault. Sorry for this. You have to add cos theta. Again, here you have to add your cos theta. And here again you have to add your cos theta, and here you can add your cos theta, but in final expression I will write this because that will cause misconceptions to a lot of people. Okay, so you can write I thetas, and okay, I theta, and here it will be cos theta and sine, 1 minute, sine theta d theta. Okay, so this is how we are going to define out the net flux. So in this particular video, we have learned about that what exactly is the equations. And if you're asking that what is the meaning of these equations, or you can say that what this equation will play a role in our future learning of the astrophysics. So the thing is that is very important because the next topic is going to be on the equation of transfer, which means that how the radiations decreases or increases, whatever is going to happen when it passes through a certain medium. So I was thinking to also explore some more topics in this particular video, but due to time limit, here I have to stop the particular video. So in the next video, we are going to generally discuss about some more advanced stuffs, like first of all, what is phase function, because phase function is very important. So let me write here that some of the important topics that we are going to write is phase function tomorrow. So tomorrow our target will be to learn what is phase function and all that stuff. Because phase function is very important, we are dealing with the scattering of the radiation inside the medium. Okay, so it's phase function. So here I've started Astrophysics series, and if you're thinking about what about the quantum mechanics, so then I will do 4 to 5 videos on the astrophysics. Then I will may upload the quantum mechanics on the perturbation theory, because I've recorded 1 or 2 videos earlier about the perturbation theory, but I'm planning to just upload it on after 5 days maybe. For now, thank you for watching my video. And if you have any doubt related to this particular concept, just write down in the comment section. So thank you for watching my video.